A steel 311Y petrol chainsaw features a two-stroke engine, a carburetor, an oil pump, and an electric ignition system. The chainsaw takes in the fuel-oil mixture and air. The carburetor mixes air and fuel, then sends the mixture into the piston inlet. The piston head raises, compressing the mixture and increasing pressure. The spark plug ignites, and the engine is started, which moves the chain for maximum sawing power. We will be focusing on the carburetor today. The carburetor consists of the Venturi, butterfly valve, and inlets of air and fuel. The carburetor provides a constant fuel-air ratio to the piston. A basic carburetor also contains a throttle and a choke. However, this chainsaw model does not have a choke, probably to reduce the smoke and pollution that comes from choking the airflow and allowing a richer mixture. This chainsaw does have a primer, which injects fuel directly into the engine for easier startup. The carburetor has a cylindrical body, with a larger outer diameter and a kinked portion with a smaller diameter called a Venturi. The throttle is the butterfly valve that comes after the Venturi. Before we open the butterfly valve to take in air, we use the primer to inject fuel into the engine. We then open the throttle valve. Air gets sucked into the Venturi, which speeds it up and causes its pressure to drop. This drop creates suction on the fuel pipe, drawing in fuel from the reservoir. When the throttle opens, air and fuel travel through the carburetor and into the piston inlet.
Now to analyze the operation of the carburetor. Because we didn't have a choke, we couldn't begin by analyzing the pressure changes from the choke. Thus, we chose to analyze the mass flow rate of the fuel-air mixture going through the system. The mass flow rate was determined at the piston inlet. Since it is a closed system, the mass flow rate into the piston chamber is equal to the mass flow rate out of the carburetor and the mass flow rate into the carburetor. The change in volume in the piston chamber during one rotation was determined by measuring the diameter of the cylinder body, then holding the piston in place and rotating the camshaft to find the maximum and minimum heights of the piston head, so we could find the changes in height and the effective maximum displacement of the engine. We determined the average density of the fuel-air oil mixture by researching the average ratio between the three fluids in a petrol engine and the average individual densities. Using the steel chainsaw manual, it was determined that the engine RPM is 9,500 RPM. Combining these three parameters, the mass flow rate of the fuel-air mixture through the system was determined to be about 0.342 kilograms per second. The main fluid mechanical aspect of a carburetor is the exchange of pressure and speed due to the geometry of the Venturi, which allows the fuel to be sucked into the carburetor and mixed with the other reactants. This pressure change in the carburetor was determined using the mass flow rate and the change in inlet and outlet areas due to Venturi.
Beginning at the inlet of the carburetor, the inlet pressure could not be assumed to be atmospheric due to the pressure having a non-negligible velocity. Therefore, the inlet pressure was determined using a Bernoulli equation analysis of a streamline that starts outside of our system where fluid can be assumed to be stationary and at atmospheric pressure. Through this analysis, the velocity at the start of the carburetor inlet was determined to be about 20 meters per second, and the static inlet pressure was about 0.883 atmospheres, right at the outer diameter of the inlet. We continued using the Bernoulli equation, combined with streamline and incompressible fluid analyses, to calculate the pressure and velocity changes as the flow progresses throughout the carburetor. As the flow travels through the Venturi, which first reduces to a smaller diameter, the static pressure drops to 0.543 atmospheres and the local velocity accelerates to about 39.3 meters per second. As the fluid exits the carburetor, the diameter expands a little bit more, but it's still smaller than the very start of the inlet. As a result, the static pressure at the outlet increases to 0.755 atmospheres, and the flow velocity increases to 28.8 meters per second. As a sanity check to our system, we determined the mass flow rate of gasoline of our fuel-air mixture using the ratio between the three parts of that mixture and the total mass flow rate. It turns out that the gasoline flow rate was 0.026 kilograms per second, or 0.035 liters per second. With a fuel tank capacity of 0.6 liters, our chainsaw can run for about 17 minutes nonstop at 9,500 RPM, which is reasonable given that the average runtime of a modern gasoline chainsaw is anywhere from 15 to 40 minutes. This proves to us that our system, even if analyzed with potentially imprecise measurements, is still grounded in some level of reality with easily checked performance measures. Likewise, our pressure distribution makes sense for the throttle itself to function properly, as our static pressures range in order from 0.883 to 0.543 to 0.755 atmospheres. All of these pressures are lower than atmospheric pressure, so this means that air will naturally want to travel into the intake, and the pressure at the inlet of the carburetor is greater than the pressure at the outlet, so once the fuel-air mixture makes it that far, it will only continue to travel straight into the engine itself, leading to a functional combustion cycle and thus an operational chainsaw.